Hi there. So today I'm going to talk about positive predictive value. And the reason I'm covering this is, well, it's interesting, but the reason why it's interesting is that often, there's so much focus on controlling type 1 error, which is important, but often when somebody has an underpowered study, say with 20 subjects or fewer, or even 30, it depends on your analysis. But you have how many subjects would be paired with an underpowered study. But sometimes people will say, well, I'm using really strict control on my false positive rate, so if I get a result, then I don't need to worry because I have done my due diligence and controlled my false positive rate. And that's true, it's good, that's an important thing. But whether that's the only thing we should be worried about is a whole other story, and that is where positive predictive value comes into play. So a good paper that goes into more detail about this is this Why Most Published Research Findings Are False. This isn't really an overview of that paper. I'm not going into the same amount of detail. I'm basically going over the definition of positive predictive value and showing one table. So sorry I don't have the journal here. I'm blanking on what it is, but if you Google it, you'll find it. It's all over the place. So here's your scenario. You run a study and you analyze your data and you find that a result survives p less than 0.05 corrected. And what is your hope? So again, let's say you've used, you didn't just go with, you're very careful. If you use random field theory, you made sure your threshold for the cluster forming was really high as recommended by Eklund, or you used a non-parametric approach, a permutation test. Either way, you feel pretty good that you're really controlling things at 0.05 corrected for multiple comparisons. So you're on one end, as I mentioned earlier, you might be saying, well, I've used really good false positive control, so there's only a 5% that my result is a false positive, right? That is exactly right. But whether this is our only concern is the question. What you might actually want, if you stand back and think about, if you run a study and you find a result, you don't want it to be a false positive, but another aspect that you might be concerned about is the likelihood that your finding reflects a true effect. And these are actually two slightly different things. And positive predictive value, the false positive control is what this first one deals with, and we hopefully know all about that now. If not, go read the Eklund paper, and I've done videos on that as well. But what about the second thing? The likelihood that our finding reflects a true effect. So that is what positive predictive value relates to. And it is the number of true positives divided by the total number of positives. So it's very different from the type 1 error rate, and it's just focusing on a different thing. So the proportion of those significant findings that are actually significant. So I'm going to explain how we get that using this 2x2 table, which I've used frequently in videos when I was going over power and type 1 error rate in previous videos. We've seen this. So let's assume we have a bunch of voxels. So the voxels will either it'll be the case where this truth that we don't know, either the null is true or the null is false. And then we have our test result, which corresponds to the rows. Either we'll reject the null or accept the null. This is a bit of lazy wording. I should have said fail to reject the null because we can't actually accept the null using frequentist statistics. You can't say, oh, there's no effect. I can't stress that enough because sometimes it's tempting to set up your study that way, and you want to show that two treatments are the same, and we really can't do that. So we can't show the null. Anyway, so let's say we have 1,100 voxels, and the oracle tells us that 1,000 of those voxels are truly active, are not active, the null is true, and 100 of those are actually, they have signal in them. If I have a 5% error rate, which is what we use, and this isn't, I'm not talking about family-wise error control, let's just do a per comparison error rate control. So if I have a 5% type 1 error control, that means 5% of my 1,000, or 50 voxels, will be deemed significant, when in fact so we're rejecting the null, but the null is true. That is our false positive. Given the null is true, we've rejected the null. So that happens 5% of the time. So the ratio for false positive rate, the denominator is 1,000, the numerator is 50. If I have 50% power, now we're going to focus on this column because power is the denominator is at the number of voxels where there is activation, which in this case would be 100. And then we have 50 because 50% of 100 is 50. So again, type 1 error rate, alpha, corresponds to this cell, power corresponds to this cell, type 2 error is the cell, and then this is just, yay, we correctly failed to reject the null when we should have. So again, the 5% for type 1 error rate comes from 50 divided by 1,000. The 50% in this case for power is 50 divided by 100. So what's positive predictive value? So positive predictive value, and what does it require you know? It requires knowing these two numbers. It requires you knowing how many tests were false positives and how many were true positives. And because the positive predictive value, again, I think I'm going to have the ratio again, that's out of the things we found significant. So now we're actually focusing on this row, the ones that were correct. So we need to know both of these numbers to know how many were rejected, but we also need to know them individually, not just the sum. Okay, so what information do we need to know to figure out these numbers? Well, we need to know our type 1 error rate, which we know. We need to know the power, which we can estimate, and we need to know the true number of tests that where the null is true and the true number where the null is false. So I'm going to call that number HO. So number HO is the number where the null is true. Number HA is the number where the null was false. Then to get this number, you just take, remember it was 0.05 times 1,000, so the error rate alpha times the number where the null is true. And likewise, you take the power, 1 minus beta, times the number where the null is false, and that gives you this value for this cell. And then you just sum these to get the total number of rejections. So this part here is simply the sum of this plus this. Okay, so positive predictive value is, I should have put it in words, it's the number of true things that are actually true. Let me go back. Positive predictive value, you want to take this cell here, which is the number of findings where you rejected the null and the null is actually false, so yay, we did it right, divided by the number of times we rejected the null. Okay, so that is positive predictive value. So I'm going to take this value divided by this sum. So that's the proportion we're interested in. Again, just to compare that to type 1 error rate and power, type 1 error rate, the denominator was this number, power, the denominator was this number. So now we're focusing on the row for positive predictive value. So the number of times the alternative is true times the power over the number of times the null is true times the type 1 error rate plus the number of times the alternative is true times 1 minus beta. So again, the numerator is the number of times we rejected the null correctly, and the denominator is simply the number of times we rejected the null. So relating it back to the word definition I had, it is the number of, it relates to the proportion of times we reject the null, we've done so correctly. So now it's just some simple algebra. I did not divide the numerator and denominator by the number of null. So this becomes this ratio, number of alternative divided by where the alternative is true divided by number where the null is true. If I divide number of null by number of null, it just cancels out to a 1, and then I have number of alternative divided by number of null. And they call this ratio R in the paper. R is the odds that the probe effect is non-null. So it's just an odds. So this is the definition that you'll see for positive predictive value. R times the power divided by the type 1 error rate plus R times the power. So you actually need 3 pieces of information for this. Again, power we can kind of estimate. We have more strategies for that. Type 1 error rate alpha, we typically know that. And R is the most difficult part to estimate. So let me show an example here. Let's assume 1 in 5 effects is truly non-null. Then R is going to be 1 divided by 5 minus 1. 5 minus 1 because 1 in 5 effects is truly null, or 1/4. And let's assume our type 1 error rate is 0.05. So here I'm looking at positive predictive value as a function of power. So you can see if you have low power, if you have 20% power, the positive predictive value is only around 50%, which means half of the time the result you find won't actually be true, right? And obviously as power increases, this increases as well. So the goal is to have, obviously, as high of a positive predictive value as you can. Of course, you can redo this plot by fixing power and varying R, and you'll get a similar thing. So the tricky bit, again, is computing this R. Due to p-hacking and other issues, it turns out that more of our published findings, which is really all we can see, and that's what we need to estimate R, there are going to be more positive results there than there should be. So R is going to be biased to be larger because it's going to make it look like it's easier to have a significant effect. So the true PPV will be much smaller than it appears. So I'm just showing a little bit of a table because I didn't want to overwhelm you. So this is table 4 from that paper, why most published research findings are false. And this is the PPV of research findings for various combinations of power, which again is 1 minus beta, ratio of true to not true relationships, which is the R, and the bias. So the bias here is the bias in computing R. So they have a second equation, which I didn't put in here, that incorporates this bias term. And I just didn't because there's, I think it's good if your takeaway from this is just the standard PPV equation. So anyway, here we have 80% power. R is 1:1, which is really promising. Or, well, no. Right. And U is 0.1. So an adequately powered, and this is the example, randomized clinical trial with little bias and a 1:1 pre-study odds will have a really high, nice PPV of 0.85. So, oh, I should have had the example with bias included. If there's no more bias, that means that this R that we have is off and that the PPV will drop. So that's with 80% power. Now if we go down here to 20% power, R is 1:5. So in other words, the ratio of true to not true relationships, it's that 1/4 that I showed earlier. There's a little bit of bias, low bias of 0.2. So it's underpowered, but well-performed phase 1/2 randomized clinical trial. The PPV is 0.23. So then they do the same thing, but the bias is stronger. And now you can see that the PPV drops. So the takeaway from this is that PPV, it is a useful calculation, but we have to take into account this bias because it does have an impact on the positive predictive value. Here's the rest of the table. Actually, I don't even know if this is the full table. I probably cut some out. So here we have really high power, 2:1, more bias. So this is a confirmatory meta-analysis of good quality RCTs, and the PPV is high. So you can see this ratio here is now 2:1, which means you get 2 true results for every not true result. So anyway, and then obviously as the second number increases, the PPV drops. So this one compared to this one, we have 0.17 versus 0.0010, and that's because this R ratio is the second number, which is the not true relationships, is so large. Okay, I will let you look through that more on your own, or you can pause the video and look at that more closely if you would like to. So the takeaway from this is basically I wanted to draw your attention to this other measure, positive predictive value. Again, of the significant findings, what proportion are real? And this paper argues that most studies likely have PPV far below 0.5. So that would mean only 50% or less of our significant findings are actually real. So I think this is really interesting, and it's good to have this in your pocket if somebody's like, well, I use 5% error control, so I don't care that I have a small powered, well, really low powered study. You really need to still care about power, even if you're using really stringent false positive control. That is all I have for this video. Thank you for your time. Please join the Facebook group, or you can follow on Tumblr or Twitter, or all three. And if you have anything you wish you knew more about, just leave it in the comments around the Facebook group, and I can cover that topic in the future. Thanks, and have a good day.